Hello again, it's me, Jesús Ortuño, once again. In this video, after what we've been checking for the past, we are going to walk you through the work we've been doing in the European project, the RethinkAction, specifically related to the land use mapping and how to use this data and how this supports the climate action plan. In the previous video, we learned how to access climate data and how to downsample that data to be useful and usable for our goals. In this module, we'll focus on one of the building blocks of the platform, the high-resolution land use maps and the historical land use analysis we've developed for the 6 different European regions that we are covering in RethinkAction. Why land use? Well, because how we use the land for agriculture, cities and energy, and our conservation has a huge impact on the climate change, both in terms of emissions and resilience. And because good planning starts with good data. Let's dive now along the methodology. Here you see a simple sketch on what we did or how we built this land use map. Our goals was to create high resolution land use map for the 6 and diverse case studies region across the Europe. These maps are essential building blocks for later analysis used in simulation, scenario planning and policy support. So quality and accuracy was and are key for this. We primarily use Sentinel-2 imagery, so from the Copernicus program, which provides a rich and multi-spectral imagery that goes from 10 meters spatial resolution. Well, for those that don't know, the Copernicus program is an EU Earth observation program that provides free open data from Sentinel satellites for the constellation of Sentinel data and in situ sensor to monitor environment, climate emergencies and security via operational services. It's run by the European Commission with the ESA, the European Space Agency support. We use Sentinel-2 for all the cases, but in the case of the Azores, the cloud were persistent, so it made Sentinel-2 less reliable because we had less frequency of clear imagery. So we combined those with Landsat data imagery to get a clearer view. So Landsat comes from NASA program, for the Earth observation programs from NASA, but we harmonize them and we combine them to provide a proper scenario for analysis. We generated a seasonal composite for each quarter between 2021 and 2022. This allows us to capture the phenological cycles, which is crucial for distinguishing between different land cover types, like irrigated crops, dryland farming, or shrublands. Okay, here in the screen you are seeing the spectral indices. The bands. The idea here is to enhance our classification. We calculated several spectral indices from each of the trimesters. We use NDVI, which is a common and standard Earth Observation Index or Remote Sensing Index, which stands for Normalized Difference Vegetation Index for measuring vegetation health. We have also calculated NDYI, which is the Normalized Difference for Water Index, for water context. The BSI, which is for bare soil. Then others like NDMI for Normalized Different Moisture Index, and NDSI for the Normalized Different Snow Index. All processes was done by using Google Earth Engine. This allows us to calculate huge amount of data and process it and all combined. The result was a multi-layer data store combining 40 spectral bands and 24 index-based layers, 64 channels in total. So those were used as an input for the classification. We created this supervised, let me check and move the screen. We created this scenario and we are using, rather to use a pixel by pixel approach, we adopted a more sophisticated method called GeoBaya, which stands for Geographical Object-Based Image Analysis. This simulates how humans interpreted shapes and spatial context in an image. We segmented the images into homogeneous regions. We use then random forest classifier trained automatically with on which extracted some sample points based on existing reference datasets like Corinne, Urban Atlas, and other local land covers. So we trained those sample points, and we also incorporated auxiliary data like OpenStreetMap for detecting solar installations and Natura 2000 and forest management dataset that were provided for the local colleagues for this. For each of the case studies, we produced two maps, two versions of the maps that you saw before. Level 1, it's called, with 12 basic land use classes like forest, crop, urban land, and level 2. In this case, for level 2, we have 21 more detailed classes. For instance, we break down, for instance, as an example, in level 2 we have for urban land we have continuous, discontinuous, industrial, roads, etc. To validate our classification, we use more than 10,000 independent validation points across the 6 case studies. We had a really good results, and the accuracy level was quite high, and that's quite remarkable, and we were able to produce the maps that you'll see now. Well, this is a close-up of one of them in the Valle d'Aosta, but also as you can access to the platform and check for the rest of each of the scenarios. You will have there the land use at level 1 and also the land use at level 2. And let me, if you would like, I can wrap up. Okay, if you want, I can wrap up with a comment on the highlight we experienced in the maps overview that I can provide. Despite their very different landscape, from forest, mixed agriculture like in Gotland or Hungary, to alpine terrain like the one map that we just saw in the Valle d'Aosta, or Mediterranean hotspots like Almeria or remote island has the Azores, we achieve high classification accuracy, as I was trying to comment before, more than 85% to 91% in most of the cases. And these harmonized maps now provide the basis for scenario modeling and especially policy support across the Rethink platform. So be sure that you check this after this video.